Hello and welcome to TidyX episode 87. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick, and TidyX is on Twitter at Tidy_explained, and on Gmail at Tidy.explained. And of course, you can go to the Bioengineer GitHub repo for Tidy Explained and open an issue if you'd like to get in touch with us there, or you can head over to the YouTube channel, like and subscribe, drop a comment, and we will be sure to get back to you.
Yep, and then if you like what we're doing, we also have a Patreon page, patreon.com/tidy_explained. If you like what we're doing, like to contribute to us to keep it going, we'd really appreciate it. We do this out of the kindness of our hearts and for fun. So, yeah, we'd love that. So, episode 87. So, we ended our series on machine learning in the Tidy Models framework last week with Julia Silge. That was a ton of fun. So, now we're going to be doing a couple of random episodes just around the holidays. Just things are a little bit busy for us. And so there's actually a really cool thing going on right now called Advent of Code. And so Patrick had never heard of this before, so I'm having a great time sharing with him what this is. So I'm going to quickly drag this over, share my screen so he can see what we're talking about, and we'll get this thing going.
Yeah. Of what I've gathered in my first time looking at the website and trying some of the little games and earning myself some gold stars, is that it's basically, it's sort of like each day for 25 days, a new task is put out, and it's in the form of like a game, and people rush to see who can complete it the fastest, and then they get added to the leaderboard. And it was started by some gentleman named Eric Wastl, who's a software engineer, I believe. And it's super cool. It's like little brain teasers. If you like this kind of stuff and it's not around the holidays, it kind of reminds me of, there's a book called Guesstimation. And it's like, Guesstimation is like each chapter is like trying to get you to think about a large number problem by chunking it and breaking things down and stuff like that. So pretty cool, though. These are like little teasers that basically are there to help you upskill your coding game, I guess, right?
Exactly. Yeah, it's I think it's kind of fun because it poses a different type of problem that you might normally come across. At the very least, there's 25 problems that Eric comes up with himself that are going to cover the gambit of different types of programming problems, it seems like, so far. So you might be really familiar one day with how to solve a problem. You're like, oh, I got this, no problem. But then another one's going to be totally different. And so I've been enjoying participating when I have time to do this. And so we wanted to pick one example where I felt as though, as our programmer, both this gave us, this problem was an interesting problem, but it also, the solution to it was maybe not super obvious, or the obvious solution isn't the efficient solution, which is often the case, but it's the efficient solution is not a big difference. You just have to slightly shift your thinking about the problem from the way that they pose it to get to the solution.
Yeah. I also like that he comes up with each of these on his own, and like the details of the stories of the problem you're solving, like lanternfish swimming in the ocean. Like if I was coming up with something, I don't even think I'd be like, yeah, totally. Like, let me write this little story about lanternfish.
Exactly. So this is day 6. So if you are intending on participating in Advent of Code and have not solved day 6 yet, maybe pause this video right now, go and solve day 6, and then come back and see how we solve this and compare your solution against ours.
Because spoiler alert, the answer is
we will have the answer here. So, but yes, so the way that this problem is posed is you are there's a whole backstory to the advent of code. It's kind of got the problems are all kind of related to a series of problems that they're going to have you solve, and there's a big overarching story. But the idea is that you're in the ocean and you see a bunch of lanternfish going by, and you're observing that they're spawning rather quickly. In fact, you might say exponentially. And so you know nothing about it, but you make some assumptions about the lanternfish, and that is what becomes the problem here, which is first that the lanternfish creates a new lanternfish every 7 days. So that lanternfish, after 7 days have elapsed, it will create a new lanternfish. The next piece of the information is that the lanternfish that was just created, all the lanternfish aren't necessarily on the same counter day. So one lanternfish might be only 2 days until it reproduces. Another lanternfish might be 7 days. Another lanternfish might be 1 day. So there's a variety of different times that you've got to kind of keep track of. Finally, the new lanternfish takes a little bit of time before it's able to create new lanternfish. It actually takes 2 additional days before it can start its counter, basically. So rather than creating a new fish every 7 days, it creates a new fish every 9 days. And then during that first 9-day period. And then it does it every 7. And so there's a lot of different things you kind of got to keep track of while you're going through. And so you can read through this, but there's kind of a lot of details here. He provides an example that you could solve. So one way that you can go through and code this all up is you come up with your own solution. You can functionalize it, then take the test data that Eric provides and throw it into your function or into your code and see if it compares against the answer that he provides, so that you can make sure that you're going on the right track. Because all that is to ask, given a set of fish with some parameters around them, how many lanternfish will there be after 80 days? So let's go and solve that problem. So let me bring up my R session here, and we can go through and do this. I also like this problem because it kind of lended itself to the R solution as well. Some of these problems are very not R related or not easy to solve in R. So
yeah, okay.
And also, I'm going to solve this with base R. I'm not going to use tidyverse this time. So that is a unique problem as well. So this is just creating the reference folder, which is from the GitHub or on my computer here. So the input file is the file I downloaded from the Advent of Code website, which has the lanternfish data in there. So I can just quickly open that up. But as you can see, it's got a number of entries here. They're comma separated. So I'm going to read in that line. I'm going to use str split and split on a comma. And then I'm going to pull out that first entry there because it's only one row of data that we're pulling out from there. And I'm going to convert them into numerics. So we end up with a vector of the counts for all the fish of how long.
We start with 300?
Yes, I believe we start with
looks like 300. Yeah.
Yep. So we start off with 300 fish. All of them are at different states in their reproducing timer.
Yep.
And so the first solution that you might think of would be to solve it the way that the problem is posed to you, which is every day, at the end of the day. So you're going to feed in a vector. So I'm going to write functions to solve this. Sorry, stepping back for a second. I'm going to write a function to solve this because it's the same problem for 80 days. Or it's the same sort of thing is going to happen for 80 days. So let's just write a function to do that, and we're just going to loop for 80 iterations, and that'll give us the final result. So the first solution is, okay, we're going to have a function. We're going to call it iterate day. It's going to take a vector, or this vector that we have here, and figure out how many new fish have been now created at the end of that day. So the first piece that we need to do here is subtract 1 from these fishies here so we can iterate their counter down by 1. So then this 2 would become a 1, this 1 becomes a 0, this 5 becomes a 4, and so everyone kind of increments down. Now the way that the problem was posed is after day 0. So they're using the Pythonic counting. Normally in R we start with 1 and go to 7. In their counting problem here, they go from 0 and go to 6. And so that's why the numbers are all 1 off to what you're normally used to kind of talking about. So if any of the fish are less than 0, so that means they've now reproduced, I'm going to create a new vector for the new fish. We're going to use the rep function. So the rep function takes 2 arguments, a thing to repeat, and the length of the number of times it needs to repeat it. And so you can do rep 1 5 times, and so this is going to produce a vector of 5 ones. Or you can do, so it can take any, like this is a rather complicated function in its own. It's got a bunch of like kind of unnamed arguments to it, but this is the simplest way to kind of think about it. It repeats a value n number of times. So we're going to have it repeat 8, which is for the new fish, like they said, that needs 9 days in order for it to start then reproducing fish. And we're going to figure out the number of new fish that have now created new fish. And so this is the, let's add together the total number of fish that are less than 0. Because this returns a Boolean, and the sum of a Boolean vector is the number of trues that exist. Then we're going to take all of the fish that are less than 0, and we're going to assign back into our fish vector the value 6, which is them restarting their counter. And we're then going to concatenate them together with that C function and return fish. So this is a rather kind of straightforward way of solving the problem. It's just kind of chunking through it. It's not going to be very efficient though, because the way that R partition or creates the vectors in your memory is it's going to ask your computer for a little bit of memory, and the computer goes, all right, here we've now reserved this amount of memory for you. And then it's going to start iterating through and adding, concatenating this vector, the values onto it. And then once it eats up all that space that the computer has reserved for your vector, it goes, computer, I need more memory. And the computer goes, all right, give me a second. Goes, partitions a little bit more memory for you. And it then tells R, cool, I've got a little bit more memory for this vector for you. R goes, great, and starts iterating a little bit more. And then when it fills that up, it goes, hey, computer, I need more memory again. And so not only are you having the actual computations occurring, you're having system calls under the hood, the computer, R and your computer conversing and going, hey, I need more memory, hey, I need more memory. And each time you do that, it takes longer and longer and longer. I mean, granted, the scale and how quickly these run, it's very quick. Like, we can't comprehend how quickly that actually runs under the hood, but it becomes very inefficient as our vector becomes really large.
Right.
But let's quickly solve that. I'm not going to talk about this other solution in a moment here. So we're going to take our lanternfish, and I'm going to assign it to just a new vector so that I can, rerun it multiple times and not impact the original vector that I have here. And then we're going to let's just run this piece here. So I'm going to take, I also want to time how long it takes to run. So I'm going to use sys.time to get the current time. I'm going to assign that to time A. I'm going to use a for loop for every day in seek len 80. So this is going to be for those 80 days. We're going to iterate day on fish and assign it back to fish. And then now it's going to basically be looping and feed that old vector into the iterate day function 80 times. So we're going to run that, and I'm also going to take sys.time again so I can get the amount of time that has elapsed between the two. So all in all, this hasn't taken too long. We're going to run a diff time here. This took 0.13 seconds. That's so little time in our day. Not a big deal. It's whatever. Yeah. This is run really quickly. I mean, we've now generated a vector that is 362,000 entries long, though. So that's not the smallest object, that can exist. But who cares? I've got 32 gigabytes of RAM on my computer here. That's not really all that much.
Right.
I mean, I think... is it memory size?
Memory size, yeah. Mm-hmm.
What is it?
It's either memory size or memory limit. I can't recall. I think One of them
No.
allows you to assign more memory, and one of them
Yeah,
tells
I
you
was
how
trying to
much you're
figure out
using.
how large this one is. Oh, it doesn't matter. Point is,
Yeah.
it's this many entries of a vector long, so
Mhm.
not super small. But let's think about it another way, because we've been growing our vector, and we know that that is not a good way to be doing things with R. What if we were to, rather than creating a vector where each entry represents a fish, what if we were to go, you know what, we don't really care about the individual fish. What we care about is counting the number of fish that are going to be created. And the way we can do that is with counters. So, why don't we do a table where each vector, or I guess this is technically a vector, but it's a table essentially where the column represents the counts. So from 0 to 8, where how many fish have 0 days left until they reproduce, 1 day until they reproduce, 6 days, 7 days, 4 days until they reproduce. Because really this is what we care about. This is the problem we're trying to solve, is number of days until, or the number of fish that exist in the counters around that. So let's create this. Let's create this named vector here, where it's 0 through 8. And let's feed this into a new function. Let's call it iterate day table. And so we're going to do the same process, but now rather than us applying it to each entry in a vector, we're looking at it across all of them. And so what I'm going to do here is I'm going to look the names of this fish vector here. I'm going to convert them into numeric values because they're going to be character. I'm looking at them as if they are a numeric value, subtracting 1, so that way they, iterate their day down 1 and reassigning it back. And so if we were to assign this to this vector here, this would become -1, this would become 0, this would become 1, 2, 4, so like just shifting them down 1. Now I want to know if any of these fish are -1. So if there's any fish that have now, we've said they're going to reproduce, we're now going to go down this rabbit hole, or not rabbit hole, but process of, okay, now we've got to add them back into our fish population here. So we're going to create this new vector where the name of the vector is 8, and it's going to be the total number of fish that have now been created, which are the fish that were at -1. And we're going to call that new fish. But those fish that already existed, they now get to restart their counters. And so we're going to take the fish at 6, which is going to be this here, and add them together with the fish that have now reproduced, because we're not overriding the fish that are at 6, because those could have been at day 7 before. They're now at day 6. We add in the old fish that exist, and we're going to add them together and assign that back to the 6 counter. This is just some sanity checking for just rearranging the order so that it stays from 0 to 8 here. And then we're going to concatenate together the fish with the new fish. And there we go. So now we're not, rather than creating a vector and shifting all those around and growing it, we're simply changing the values within that vector to do it. So let's
Just dropping counts in buckets, in bins. Boop, boop.
Exactly. So let's run both of these now together. So we're going to iterate over the same 80 days here, but I want to compare the time it takes to run the iterate day versus using our table counting method. We're going to run that. There we go. It ran pretty quickly. Yep. So let's look at the diff time. So this first time is the time it took for us to grow our vector. This time it took 0.10 seconds. This took 1/10 of the time for it to run. Awesome. And like this was so quick, like clearly it didn't have any impact. But you can look and we got the same result, which is what matters. Right? So the logic is still the same in that we're getting the same result. But this time, rather than calculating that length of the vector, which is each element represented an individual fish, we're going to sum all the entries of that table, because that's what we care about. And so there are 23,000 fish at day 0. So the next iteration, we would have had 23,000 more lanternfish. So it can grow pretty quickly, right?
Yeah.
Because that's now 23,000 elements that you'd be adding on to your vector. That just is super inefficient. So the second part of this problem was assuming that there is no limits on like resources or anything like that. What happens after 256 days? And so we're going to solve the same. It's going to be the same problem. Really, the function, because we wrote them as functions, we don't have to change that. All we do is change the looping around it. So that's actually pretty nice. So we're going to reset things. I'm going to calculate times here. So let's just run this piece here because we're going to use the table method for that because we know it runs quickly. We're going to run this. Give my computer a second to run. All right, so it's now run through this. And we get a time duration of 0.02 seconds this time. So
basically like 300ths of a second,
yeah.
0.0.
So faster than the human reaction time. This ran rather quickly.
Yeah.
Now let's try to run the growing vector solution to this. Okay, so it's running. It's running.
Still running.
It's still running, and it's going to continue to run for a really long time. The reason for this is, as we keep on saying, is the efficiency that it takes for it to run, because we have the solution here, and it's this big number. Let's actually remove the as character, so you can see R automatically converts this into scientific notation for you because it's such a darn large number. I think Patrick and I were taking a look at this earlier, and it's 1 trillion, 639 billion, 854,996,917 lanternfish. So
lots of fish.
Lots of fishies. And a really, really, really long vector. I think this is actually longer than a longer vector than can exist in R. Even with
really?
64-bit. I think. I'm not sure. Don't hold me to that.
Yeah.
I know that there is a limit to the actual length of a vector.
Right. Okay. Interesting.
Because just like the way computers work.
Like if you did a sequence from 0 to 1, length out 163985, we'd be able to see if it.
We could try. I don't want to crash. I
No,
guess we can try.
crash.
I guess it would be cannot allocate vector.
It probably would just give you an error, yeah. Or repeat a value.
Large vec. And let's assign it ones.
Yeah.
Cannot see. So yeah.
In order to do this, you'd have to probably. I wonder if you use memory size or memory limit and just set a new size or limit. I wonder if you would even have enough to. It's one of these. So if you did size equals, and just bumped it up a whole bunch.
So this is the amount of megabytes that I have.
Yeah.
So
yeah,
I physically cannot.
You're not going to get up high enough.
You're talking about 12,000 gigabytes.
Gigabytes, yeah.
Apparently, I don't know. I don't know if that's the actual size there. So I guess we're kind of waffling here. But I guess the point is to say, you can solve a problem a couple different ways. You can solve this problem 2 different ways, but one of them becomes just it's a little bit slower. B, once you start moving into a larger number, your solution is actually just you can't calculate it.
Yeah,
it's too big. That's right. And I thought this was a really interesting problem to bring up because this isn't the type of problem that most of us are going to come across, but it's just something to think about. And know ways that you can solve the problem where they pose it as, build a vector and solve it out that way. Well, that's not the efficient solution.
Yeah, that's not going to work.
So with that's that, cool. I guess we can end it here. We've talked 25 minutes about building vectors.
Next week we'll we both picked a different one. So next week I'll do mine, which will be a different Advent day, and we'll we'll go through a different problem, I guess.
Yep. So let us
Yeah.
know if you like this, if you want us to do any different problems or solve any different Advent of Code puzzles or puzzles that you've come across and think are interesting for people to solve. And with that, we'll call it. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick, and Tidy Explained on Twitter, Tidy_explained. Tidy Explained on Gmail, tidy.explained@gmail.com. You can open an issue on the GitHub repo. You can get in contact with us on YouTube. Always grateful if you could like and subscribe. You can, of course, if you really enjoy our stuff, purchase us a coffee via Patreon, or maybe we will use the money to get eggnog, whiskey, beverages, something festive.
Exactly.
Always happy for that, but no pressure if not. We do enjoy doing this, even if it is our own time. It's a labor of love. So
Exactly.
We appreciate it, and we'll be back next week, I guess.
Yep. All right. Thank you all so much, and keep on exploring your world.